Okay, so then thanks. Let's proceed with the final talk of this morning, given by Naina Ralaivaosaona from the, I'm sorry for the pronunciation, and from the University of Stellenbosch. And he will speak on the number of sources and isolated vertices in random directed acyclic graphs. Sorry again.
Oh, it's no problem at all. I've gotten used to that. Okay, so I'll be talking about the number of sources and isolated vertices in random acyclic digraph. Okay, so well, I'll talk about digraphs again. So what are the digraphs that we're considering here? We're talking about label digraphs. So the digraphs are on the vertex set 1 to n, and we're not allowing loops, and we're not allowing multiple edges. So what do I mean by that? Well, in Svante's talk earlier, it's well, he called parallel edges maybe. So we are not allowing this red stuff here on the left, but we are allowing the green ones. So it's edges that go into opposite directions. So here's an example of a digraph. Okay, so what are acyclic digraphs? So say directed acyclic graph or DAGs. So you are not allowing directed circles, so directed cycles. So the graph that you see on the left, I generated from Sage, is not a DAG. As you can see down here, you see a directed cycle. And there's quite a few of them over here as well. There's one, but the one that you see on the right, although there seems to be quite a few potential cycles, but all of them passes through 6, and 6 is a source, so they are not directed cycles, so you cannot really go around. So that's a DAG, the one you see on the right there. So the simple question is, I give you n, generate one at random. What can you say about them? Or maybe you could maybe add condition on the number of edges, edge density, or arcs, if you like. So there aren't really that many results about that in the literature. There are other random DAG models out there. I've listed a few here. Perhaps you know more. I apologize if I did not list them here, but many of these models rely on ordering on the ordering of the vertices. So and if you look at these models, um, the acyclic property is really just a consequence of the order of the vertices. So over here I said a directed edge from I to j is only allowed if I is greater than j. Some other people consider the other way around, but that's really just equivalent. So Carter and Newman even say that in their paper in 2009 that we should maybe call these random DAGs because that's misleading. We should call this random order graphs, but they say it's already too late. People are using random DAGs. But on the other hand, there are quite a lot of uniform random generation algorithm out there that generate DAGs. So I've listed a few results here. Okay, so we are interested in random DAGs, and hopefully the acyclic property should not. We're not following this model that I mentioned here. It's not order. It's not the acyclic property should not follow from the order. So we don't care about the order of vertices. Okay, so what model are we considering then? We generate I think the natural binomial model for digraphs. So you choose a p between 0 and 1, and for each of the n times n minus 1 possible directed edges, for each of them you choose each of them with probability p independently. So you get a digraph, and what you do is you just simply condition the digraph to be acyclic, and you have this model that I call DAC. Okay, so based on the construction, if you choose p equals half, then what you get is the uniform random DAG. So no restriction on the number of edges. So you put all possible DAGs on n vertices, and then pick one at random, and that's what you get if p is equal to half. So this is sort of the sort of a natural model, um, and that's what we're going to consider. So the question is, how do these guys look like? So so how do these random acyclic digraph look like? Um, and well, the things that we're going to look at today, well, we're going to look at the number of sources, or equivalently the number of sinks, or isolated vertices. Um, I'm not going to talk about height, but that's something that is also interesting to look at. But the reason why I mention it here is because if p is equal to half, when you just pick up a random acyclic digraph at random, then Liskovitz proved that the number of sources, so sources are the vertices within degree 0, the number of sources has a discrete limiting distribution with mean 1.488, and that number occurs several times when you study a cyclic digraph. Mackay 1989 proved that the height is asymptotically normally distributed with linear mean invariance. So you can imagine that if you pick a DAG at random, you put all DAGs on n vertices in a basket, pick one at random, then it looks like a very long, long chain. So the height is about n, and the width is a constant. Oh, well, not really a constant, but bounded. So okay, so but we are interested in the case where p is of the form lambda over n. So in a sparse case, the reason why we want to do that is because we know that there is in random digraph, we know that there is a phase transition around 1 over n, and it would be interesting what happens to the natural parameters when we go through this phase transition. So let's go back to a couple of years ago. Myself and all these people, De Panafio, Dogval, Rasendasen, and Wagner, we proved um, this theorem. So remember that the model is generated a random digraph, and then condition that the outcome is acyclic. So the natural question would be, what is the probability of a digraph being acyclic? And that's something that we answered a few years ago, and this it's of this form. So you can see here the phase transition. If lambda is less than 1, then you have a constant. Well, constant, but depends on lambda. And if lambda is 1, the critical phase, what you have is a constant times n to the power minus 1 over 3, so it's polynomial. And if lambda is greater than 1, as expected, this probability is exponentially small. So you see a phase transition, but now we want to study what happens to the what is the property of a random acyclic digraph. If we condition that the digraph is acyclic, what can you say about it? Okay, so here's our first result. So we looked at the number of sources, which is perhaps one of the most natural characteristics of a DAG. So if we denote by S of D the number of sources in this an acyclic digraph D, then we proved that the expected value, so if you generate a random DAG, then expected value is a constant times n. So it's linear in n, and it satisfied the central limit theorem. The average, the constant in the average is of this form. So there's a change as expected. So if lambda is smaller than 1, then what you get is exponential minus lambda. That's not entirely surprising, because that is what you would have obtained if you simply calculate the number of if you calculate the number of sources, the average number of sources in the unconditioned digraph. And that's what you get when lambda is smaller than 1, and and a random digraph with a positive probability is a DAG. So and you know that the number of sources will be concentrated about that value times n. So it's not entirely surprising that you get exponential minus lambda there. But right after the phase transition, you get 1 over e times lambda. So it sort of grows very slowly, decreases very slowly in terms of lambda. Well, that's fine too, because you know that a DAG, um, well, I know that lambda is fixed, but when you think about it, when lambda is very large, a DAG will always have a source, at least one. So it kind of explains that this should not really go to 0 very fast in terms of lambda. All right, all right. Since we are dealing with sparse graphs, a cyclic digraph, we can also consider isolated vertices. And the isolated vertice satisfies a similar theorem. So the expected value is a constant times n, and we also have a Gaussian limit law there. The constant in the expectation is as follows, and as you can see, in a critical and supercritical case, you have the exponential function, exponential of minus lambda plus 1. So if lambda grows, this goes to 0 very fast, and that's expected because, well, if lambda is, although we assume that lambda is fixed here, but if we assume that if lambda is allowed to move with n, if lambda is about log n, we are not expecting any isolated vertices anymore. And so that's sort of a, you can see that in this formula. All right. So how do we prove these theorems? So we consider generating functions. So when you study digraphs, you consider what is called a graphic generating function. So let me just explain what do I mean by that. So let's say you have a class of digraphs, call it A. Okay, so and so we consider the following polynomials. So alpha n, so n is fixed, and alpha n of y is the sum over all digraphs in that class of y to the power of the edges. This is the number of edges in that particular, or arcs in that particular diagram. So we consider that, and the graphic generating function for that particular class, it's a bivariate generating function. X counts the number, indicates the number of vertices, and y indicates the number of edges. But what you have is the alpha n y over here, x to the n over n factorial. But then there's this term down here, 1 plus y to the power n choose 2. And why do we consider such a generating function? Because of the following. So let's say you have two classes of digraphs, and you combine them in this way. So if you have an element of A on the left hand side and an element from B on the right hand side, and you are only allowed to connect elements from A to B with the red edges that go only in one direction. So in this particular case on the picture, it goes from the left to right. If that's the only thing that is allowed, then you get the elements in the class C. Then we say that this is an arrow product between the two classes. So C is the arrow product of A and B. And if we convert the graphic generating function, what you get is the product of the graphic generating function. So the generating function of C is the product of the generating functions of A and B. Okay. So that's the reason why we consider graphic generating function for digraph. Okay, so if you say, let's say we are going back to acyclic digraphs, and we want to count the number of sources. So what you do then is you can consider an arrow product. So on the left hand side we have the empty digraph, so no edges on the left hand side. But on the right hand side you have a DAG, and you are allowed to build, you're allowed to have edges that goes from the left to right only. So we have that arrow product. So, well, if that's the case, then you have a DAG where the stuff on the left hand side are sources. So, well, that's not necessarily all the sources of the DAG, because over here there is a source, but it's a subset of a source. So and we can translate that into generating functions. And what we get is, well, if you consider an y and you include another variable u, which counts the number of sources, then you apply the product that I mentioned earlier. What you get is that the graphic generating function is going to be of this form, which is a nice form where it's phi of 1 minus u times x of y divided by phi xy, where phi of xy is this nice function here. So okay, so the second thing is, now that we have the graphic generating function, and how do we get a distribution out of this, of the distribution of the number of sources? Well, the probability generating function, this is the other nice thing about this. So the probability generating function of the model, so remember the model is you generate a digraph and you condition it to be acyclic. So you can get the probability generating function by replacing the y variable by p over 1 minus p. So, well, you have to take the coefficients and then we replace the y by p over 1 minus p. So it's a very simple calculation, allows you to prove this. And so it is really just, the problem is then translated to extracting coefficient and then replace the y variable by p over 1 minus p, and then you get the probability generating function. So for the number of sources, well, we've estimated the denominator in our paper in AofA 2020, and there's a much longer version in the archive now, but we can do a similar analysis for the top, with u allowed to vary in a neighborhood of 1. And we did that, and that's how we prove the central limit theorem. Okay. Okay, what about the number of isolated vertices? For isolated vertices, I just want to mention that Giselle in 1996 gave a multivariate generating function that counts, that simultaneously counts the number of sources, sinks, and isolated vertices. And we just picked that up, and we were only doing the isolated vertices case. And what we get is the following. So we do the same. So if we take if for each n we consider this a star yu, now this time u counts the number, what u indicates the number of isolated vertices in your digraph. All the time when I write this, the sum is all over a cyclic digraph on n vertices. So you consider that that's a polynomial, and what we get is, well, we don't get the graphic generating function, but we do have exponential generating functions. And the reason for that is because if you are dealing with isolated vertices, well, if you take the isolated vertices in the DAG, there are no edges going from the isolated vertices to the rest of the DAG. So that explains the reason why we have exponential generating functions here. As before, once we have that, then we get the probability generating function for the parameter we're interested in. And as before, we simply just have to take the coefficients and then replace the y by p over 1 minus p. The problem now is that the numerator, the a and star, well, it's sort of hidden in this exponential generating function, and that exponential generating function is not even convergent. So yeah, so perhaps people in the community have done something like this, but I haven't. So what I did was I calculated the coefficient from this equation here, calculated the coefficient, and what I get is that. And remember, my problem is to find a star NYU, the numerator of the left-hand side, but I can write it in terms of the right-hand side. And the right-hand side is something that I can calculate. So the denominator is something that is done already, but the numerator, I need to figure out, I need to calculate AN minus J. So so I need to, essentially, I need to calculate AM where M is less than N. So so I estimated the ratio on the right-hand side, and what happened was that this is what we get. So in this sum here, in other words, in this sum here, the terms that matters, the terms that matter are the term where J is very close to N. So oh sorry, J is very small. So of this order, so from J is between 0 and to the power 3/5. I think anything between a half and 2/3 would work, but that's what I chose. And that's the term that matters in the sum. And I calculated the ratio, plug it into the sum, and what I got is this. So the ratio is actually very nice. It's kind of a very simple function. I don't know if it's negative binomial distribution. I have no idea, but you get this, and from that you can get a central limit theorem. And that's how I prove the central limit theorem for the number of isolated vertices in a random acyclic digraph in this model. So the one thing that I want to mention is that often in the the average out degree in the unconditioned digraph is lambda. All right, and we kind of, well, we could ask the same question: what if I condition the graph to be acyclic? Well, do we still have that property that lambda is the average, the average out degree in the graph? And although I didn't do it in this paper, but the answer is probably no. So I think what's going to happen is that the average out degree, or in degree, doesn't matter, is lambda when it's a subcritical case, but when you go to supercritical case, I think it will change as well. So yes, so that's all I have to say. Thank you very much.
Thank you very much. Some time for questions. Well, then maybe I start with the small questions in the last slide.
The last slide, okay.
Last slide you had lambda is smaller than 1. If lambda equals 1/2, then A of lambda is 0. This is something that
yeah, that's yeah, of course. I didn't pay attention to that when I wrote the slide, but you get yeah, it doesn't, yeah, very good observation, but you get you can write this in terms of exponential. What you can do is you can convert this into exponential and take a tending to 0, and you get something out of it. So that's in the paper. So
you have to expand more than that.
You have to expand, and then things, yeah, and it will work out.
Okay. Other questions? From the for online community? Let's just double check. No. So a last chance. If not, then thank you very much.
Thank you. Bye-bye.